It wasn't quite 3 minutes, so I was leading you, but we should get started because I think we're quorate and everyone whom we're expecting is here. It's a great pleasure to welcome you all to our first Philosophy of Physics research seminar of the year, and of course particularly so when we have the occasion to welcome back David Wallace, such a great friend here and such a leading light in the firmament of matters physical and philosophical. So I won't introduce David at length because I've done so before and I'm sure everybody knows who he is. But it's really great to have you here, David. Thank you so much for coming. And he's going to be talking about something which is highly relevant for the philosophy of thermal physics material that many of you are doing this term. So over to you, David.
Thank you. And it's always a great pleasure to be back in Oxford. It's always terrifying how quickly the faces change. So, quick review of things I suspect most people already know. One of the central problems, arguably the central problem in the philosophy of thermal physics is what you might call the irreversibility problem, which in basic outline says, at the microscopic level, physics is reversible. Its dynamics does not qualitatively distinguish past from future. I won't need to go into the details of what that means, but in outline, it means I can run the equations forward as easy as I can run backwards. Nothing in the form of the equations really says which direction counts as forwards in time, which direction counts as backwards in time. In many cases, there's some explicit time reversal symmetry available, but even when that's not true, such as in exotic regions of the standard model of particle physics, even in those contexts, the equations don't really tell you which of the two non-symmetrically related directions is the past and which is the future. The equations are just as well set up to run things backwards as they are to run things forwards. Mesoscopic physics, physics at the scale of things like the Brownian motion of pollen grains, and even more so physics at the macroscopic level of everyday human life, is irreversible. Its dynamics made a qualitative distinction between past and future. The dynamics are irreversible, it's one way to put it. They're structured in such a way as you can run the equations forward to make sometimes probabilistic predictions about the future, but you can't run them backwards, even probabilistically. And so there's a fundamental mismatch between the way the microscopic physics works and the way the macroscopic physics works. I mean, this is often illustrated by pointing out things about the passing of time and the way age works. I tried to find a photo of myself when I left Oxford to do a comparison and show this, but I wasn't able to find a good one, so taking my word for it, there was less grey hair. This process is, alas, irreversible. Anyway, of course you could have a fundamentally disunified picture of the world, where we just didn't expect there to be any connection between the microscopic and the macroscopic, or we can imagine some fundamentally non-physical or pre-physical injection into physics that made the difference, some kind of priority of causal intervention or something. That's not an indefensible position, but I'm going to take as read for the purposes of this talk that we don't want to go in that direction. We want to hold on to the basic idea, I think very strongly supported by physics practice, that we can in some way derive mesoscopic physics from microscopic physics. And in brief partial defense of that claim, we seem to do it all the time in physics with high calculational success and make and generate a highly predictive statistical mechanics that constructs higher level irreversible equations from low level reversible equations. If we did that, then as a matter of logic, something had to go in that broke the microscopic symmetry. Microscopic symmetry. That's what I get for writing slides when you something has to break the symmetry. And there are a bunch of suggestions as to how that happens, but more or less at some level, they all come down to saying that if the dynamics is symmetric, and yet we derive an asymmetric conclusion from them, we must somehow put the asymmetry in the form of the boundary conditions. And proposals of this kind have been around for a long time, more or less as long as statistical mechanics itself has been. But in the last 20 or 30 years, they've become very widely discussed, more than anything, through the version of them and the name for them that was advocated and popularized by David Albert in his book, Time and Chance, I think extremely serious, contested for the most significant book of his generation in philosophy of statistical mechanics, one of the leading books in philosophy of physics of that period. If you haven't read it, you should read it. And Albert calls his hypothesis that breaks the symmetry of microphysics and allows us to derive these irreversibilities the past hypothesis. I honestly don't know, and found it mildly difficult to check for this talk, whether he coined that phrase or simply popularised it. But in any case, the term has become in extremely wide use, more than anything through Albert's popularisation of it. And I'll be using Albert's version of this as my target in this talk, although I think much of what I'm going to say applies to various cousins of this proposal that others have stated. But it's helpful to have a sort of clear statement to focus on. And this is how Albert sets up his picture of how we get mesoscopic, macroscopic irreversibility from microscopic reversibility. And for slightly obscure reasons, Albert, not in his book, but in later work, came to call this whole package a mentaculus. I think it's after some Coen Brothers reference, but it not being in the appropriate bit of New York, it went way over my head. And I'll just read out from the slide the section in his book that gives this. The Newtonian statistical mechanical contraption for making inferences about the world consists in its entirety of 3 laws and 1 contingent empirical fact. The empirical fact is the one about what the macro condition of the world currently happens to be. So, for instance, the empirical fact would include my actual observations of you guys in the lecture hall and my memories and what's on my laptop and all that kind of macroscopic contingent data. And the laws are, 1, the Newtonian law of motion, which is that F equals ma, and I think in context Albert also intends to include whatever the specific Newtonian dynamics are. The past hypothesis, which is that the world first came into being, whatever particular low entropy, highly condensed, Big Bang sort of macro condition it is, that the normal inferential procedures of cosmology will eventually present to us. And the statistical postulate, which is that the right probability distribution to use for making inferences about the past and the future is the one that's uniform on the standard measure, by which he means the Liouville phase space measure, over those regions of phase space which are compatible with whatever other information we happen to have. So just to cash out how that works for people who are unfamiliar with it, the idea is something like this. By itself, the Newtonian laws of motion in a, supposing for the moment, a deterministic universe, tell you very little about what's going to happen on the macroscopic level, because almost anything that could happen macroscopically described is compatible with some way the microscopic physics could work out. So bulk violations of conservation laws are going to be ruled out, but more or less any intuitively incredibly unlikely thing is going to be compatible with some set of initial conditions. So the starting idea is that we have to add something to microphysics to get any deductive power out at the macro level. Then the second observation is that, and we learn this from statistical mechanics, as long as we're interested in making inferences about the future, we get very reliable predictions out for the future by supposing that all micro conditions compatible with our observed macro condition are equally likely. But anyone who remembers the continuum infinity points in phase space knows that that has to be a slightly loose statement. The sharper statement is that we get accurate predictions about the future macrodynamics by putting the Liouville uniform probability distribution over the macro condition, over the region in phase space compatible with our macro data, and then evolving that forward under the classical mechanical equations. And so one's immediate thought is fine, we'll just add to our physics the assumption that the probability distribution is uniform over the present macrocode. And the problem with that is that that works just fine when you evolve things forward in time and fails totally if you evolve things backwards in time. So for instance, if I take a macro condition that consists of a half-melted ice cube, then running it forward in time reliably predicts that the ice cube proceeds to completely melt. Running it backwards in time predicts that the ice cube coalesced into being, and from an initially lukewarm glass of water, which it's a subtle question to say in what sense that wildly contradicts other things we know, but one way or other it wildly contradicts other things we know. And so then the thought is, we would be okay if we imposed the statistical distribution not over the present macro state, but over the macro state half an hour ago. That would sort out the ice cube. That would correctly predict what the ice cube was doing 15 minutes ago. But it wouldn't predict what the ice cube was doing an hour ago. And if we put the uniform distribution over the macro state a year ago, it would predict the physics correctly over the last year and into the future, but it wouldn't predict things before that. And if we put it back at the time of the dinosaurs, it would get post-dinosaur biology just fine and pre-dinosaur biology wildly wrong as a sort of time reverse of post-dinosaur biology. And so the logical conclusion of this line of reasoning is the only place you can put this condition is at the beginning of time. So hence the past hypothesis. You say, okay, fine, whatever the appropriate macro state at the beginning of time is, that's the macro state over which we put the uniform distribution. And then that gives us a sort of two-part hypothesis that we're supposed to add to the Newtonian dynamics to derive macroscopic physics. There's the macro state part, which says the initial macro state was, in Albert's statement, whatever particular low entropy, highly condensed Big Bang sort of macro condition it is that the normal inferential procedures of cosmology will eventually present to us. And then the statistical postulate, the micro bit, which says given the initial macro state, the probability distribution over microstates is uniform. I should say Albert states it originally as a hypothesis about the present probability distribution, but it's equivalent to a posit about the initial probability distribution. And for various reasons, I think it's cleaner to read it that way. So, so this has been widely discussed, and there's been lots of sort of foundational discussions about what sort of hypotheses these are these kind of transcendental principles of a sort of Kantian kind that underpin the possibility of physics? Are they contingent dynamical claims? Might they be explainable in one way or another? Might some of this be dispensable? Is some of it disconnected inappropriately from the way we think about our epistemology? There's really quite a large literature of this kind. But in most of this literature, one question goes largely unengaged with, which is the question I have for this talk, which is, if the past hypothesis is that the world first came into being in whatever particular low entropy, highly condensed Big Bang sort of macro condition it is, that the normal inferential procedures of cosmology will eventually present to us, what kind of particular low entropy, highly condensed Big Bang sort of macro condition is it that the normal inferential procedures of cosmology eventually present to us? And what I want to do in this talk is try to answer that question. Not finally, because presumably a final answer would depend on a final cosmology, which at present we don't have, but as a kind of interim progress answer based upon the limited but enormously impressive progress that contemporary cosmology actually has made. And I want to sort of see, in the light of what cosmology tells us about the initial state of the universe, to what extent does that cohere with Albert's framework, and to what extent is it a problem for it? And to give a spoiler alert, the answer is going to be that I think interesting details of Albert's proposal change quite substantially when we track the cosmology correctly, although I think the core ideas of Albert's framework remain unscathed by that example. So I want to start by just talking a bit more about Albert's framework and making a few points that are going to be relevant in the discussion before I actually turn to look at cases of cosmology. So the first point I want to make is to just distinguish, and this is in many ways just a rephrasing of Albert's own statement, these two parts of the past hypothesis I mentioned earlier. And I want to call these phm and phmu. So m for macro, mu for micro. Incidentally, whoever it was who did the naming conventions in statistical mechanics back 100 years and more ago and decided that micro and macro were good words for these profoundly different frameworks, given that they're often difficult to distinguish to the ear, got us into a lot of trouble. So my m and mu is partly to avoid the difficulty distinguishing macro and micro. This is perhaps because I'm scarred by my initial Oxford statistical mechanics lectures, where the lecturer had a quite thick Russian accent, which made it entirely impossible to distinguish these. Anyway, so ph macro, is the hypothesis about the initial macro state. The initial macro state is whatever sort of macro condition it is that the normal inferential procedures of cosmology will present to us. And the ph mu, is that the probability distribution for the initial microstate is uniform across that macrostate, again, with respect to the standard Liouville measure from phase space. Okay, and I want to make 5 quick points about the Albert framework. So the first is, notice, phm is a placeholder. It's a placeholder for our hypothesis about there being a specific macrostate. It's often misread that way, including in the literature. it's often read as just being the hypothesis that the early universe had low entropy. And then off the back of that, it's read as being committed to the idea of entropy as something that we need to understand to be able to make statements about the initial macrostate, and read as something that gets us in trouble insofar as the notion of entropy becomes hard to define in the early universe. But Albert is clear, I think, that's not what he has in mind. It's not simply the hypothesis that the initial state has low entropy. It's a placeholder for the hypothesis the initial state is P, which, by the way, has low entropy. So if cosmology eventually delivers us P as what it finds through its normal inferential procedures is the initial macrostate of the universe, then the past hypothesis is the initial state is P. Nonetheless, notwithstanding what I said of entropy, there is a sense in which PHM is relying on some kind of emergent high-level concept, because PHM is a claim about the initial macrostate. What are macrostates? Well, the macrostates are, in classical statistical mechanics at least, are in some sense a partition of the phase space of the system into regions. Quite what those regions should be is often a little vague in presentations of classical statistical mechanics. A first stab is often that they're somehow macroscopically distinguishable, which is obviously, not just emergent, but flatly humanocentric. A better glossing of what the macrostates are is something like there's some kind of carving up of the phase space such that I get some kind of autonomous dynamics with respect to those macrostates. So, for instance, in the canonical example of a dilute gas, the macrostates are characterized by something like what fraction of the particles have velocities inside any given range. And then the justification of that as the macrostates is going to be something like I can write down a dynamics for how those fractions change over time that's largely insensitive to what the micro details are. But in any case, the point is that this notion is, at the very least, is kind of emergent high level. And so there's going to be a not necessarily vicious circularity in this setup, where I require my past hypothesis to legitimate my macrodynamics, because remember, macrodynamics tends to be irreversible. It's only derivable from microphysics with some additional hypotheses. I need the past hypothesis to legitimate the macrodynamics, and yet the concept of macrostate that comes out of the macrodynamics is itself required to state the past hypothesis. I don't think those kind of circularities in philosophy are always vicious, but it's worth recognizing when they're there. Okay, third observation, there's a division of labour going on. I could have just merged pH mu together. I could have stated them as something like, there is a macrostate such that the probability distribution is uniform over that macrostate, and that's, with the subspecifications of which macrostate, that's the thing that's doing the work. What I ultimately need to make predictions is a certain probability distribution. What PHM and pH mu between them tell me is this is a probability distribution which is zero outside a certain region and uniform with respect to lethal measure within that region. And we'll see, as we look at some cosmology, that division of labour starts becoming a little fragile. In some ways, we might cash out the cosmological details. Fourth observation, pH mu is a probabilistic statement. And the probabilities here are understood to be classical probabilities. At least in Albert's framework, they're not just to be understood as some kind of pure epistemic ignorance. We're not simply saying we don't ourselves know what the macro conditions are. To borrow Albert's example, how can it possibly be true that me not knowing something about the macro conditions can explain why milk mixes into coffee or that ice cubes melt? So Albert wants that to be an objective thing that is objectively explained. On Albert's story, at least, the objective thing is something roughly about the relative frequencies, but a little sharper than that. So anyone who's looked at the relevant bits of philosophy of probability is Albert thinks these probabilities are the kind of things that come out of something like the Humean best systems analysis. And I won't go into a huge amount of detail as to how that's supposed to go, but just to give Albert's own sort of illustration of this, Albert says, well, suppose you get an audience with God in the morning and you ask God, tell me what the universe is like. And God says, well, there's a particle and it's at these coordinates and has this velocity. And there's another particle at these coordinates at this velocity. And there's another particle, and then you stop God and say, look, I'm sorry, this is taking a long time. I've got other things to do today. Is there some way you can give me something a bit shorter? Like, could you give me the best description of the universe you could fit on a T-shirt? And God says fine, and then on the t-shirt he puts the laws of physics, and Albert set up the Newtonian laws, and then he puts the probability distribution. And the idea is supposed to be that the probability distribution is the most succinct summary you can give of where the particles are, that's manageable in length, and yet helpful. Whether that's defensible is debatable. I think there are some quite deep problems with it. I'm not going to get into that, but that's the basic idea of what the probabilities are supposed to be in Albert's story. But whether or not the details of Albert's account are there, they're supposed to be statistical probabilities. They're supposed to be the kind of thing that's over and above the dynamics, that somehow is not stochastic, it's not a primitive injection of probability, it's something that can coexist with whatever the actual configuration is and whatever the actual deterministic dynamics are. And finally, although in many ways it blurs with 4, Albert sets this up as some statements about Newtonian physics, but there is a tension in the whole project that comes from that commitment to Newtonian physics. So if we go back to Albert's statement of the mentaculus, then the first assumption speaks of the Newtonian law of motion, and the second assumption speaks of of what's delivered by the normal inferential procedures of cosmology. Well, the normal inferential procedures of cosmology is a special part of the broader normal inferential procedures of physics, long ago delivered to us the fact that the Newtonian law of motion is wrong. And furthermore than that, because, of course, it's still very useful in some contexts, that the Newtonian law of motion is inadequate for modern cosmology. So quite how we're to think about this is kind of fiddly. And I think there's sort of 2 readings you can make of Albert. One of them is that this whole project is supposed to be a training wheels project, and that somehow it's all about how things would be in a fictitious Newtonian cosmology, and that by understanding how things would be in a fictitious Newtonian cosmology, somehow we'll have warmed up to understanding how to do it in a realistic cosmology. I don't think that's a textually plausible reading of Albert. I think really what we have in mind more is that somehow it's supposed to be that pretending the dynamics is Newtonian won't make a deep difference, and that if we replace 1 here with appropriate laws of motion from a more up-to-date physics, then the project will qualitatively continue in the same way. But I'm actually going to consider both of those possibilities when we try to work out what an actual cosmology might give us. So in fact, I'm going to consider 3 models of cosmology. The first is what you might call a Newtonian cosmology, where Newtonian dynamics is exactly true. And the Newtonian cosmology is a flat fiction. I'm not in any way suggesting it's at all realistic as a description of our world. It's just a kind of genuine training wheels thought experiment. And the second cosmology is classical Big Bang cosmology, by which I basically mean the kind of cosmological theory that seems fairly accurate describing our universe after what cosmologists call the transparency epoch. So after about 380,000 years after the Big Bang. And the third is going to be inflationary quantum cosmology, which is not by any means a universally accepted theory, but is widely accepted in contemporary cosmology and is about as far as you can get into contemporary cosmology while still finding anything that is widely accepted. But basically, the rest of the talk is that I'm going to be going through these 3 models of cosmology, and in each case, seeing how the past hypothesis works on those assumptions. So let me start with the Newtonian case. Here's my setup for my Newtonian cosmology. I'm assuming flat space, Galilean or Newtonian space, whatever you like. All of matter consists of point particles, which for convenience all have the same mass, and they're interacting under this potential, which is basically an inverse square law interaction of the form you have in Coulombic electrical repulsion or Newtonian gravity, plus a short distance repulsive force. I put a concrete form for it in the paper version of this talk, but the actual form doesn't matter. It's just there to effectively make the particles pretend to be hard spheres and to avoid certain singularity problems that occur if you either have literally infinitely hard spheres or literal point particles. So you want to think that the repulsive force here says when the particles get within some very short distance of each other, then there's some repulsion that ramps up without limit and pushes them apart. When they're not within the distance of each other, then the repulsive force could be ignored, and we can just consider that inverse potential It's naturally tempting to think that our cosmology should be an infinite Newtonian universe with infinitely many of these particles and some constant density. For reasons that various people, including some in this room, have explored, those cosmological models are troublesome. They run into various problems of prediction. So to sidestep all of that, I'm going to put them in a box. I told you this was a fictitious cosmology, so we may as well lean into the fiction. So there are finitely many particles. How many? Lots. 10 to the power of 100, say, I don't care. And the box is finite, but very big, gazillions of light years across. No light in this universe, so we're just entirely fictitious what we say the scale is. But the scale is such to allow a very, very, very large number of particles, but the walls of the box kind of constrain the singularities that happen if you have genuinely infinite setup. If you like, you can think that my universe is close and toroidal. It comes to the same thing. Okay, and now let me just state a past hypothesis in this setup. And again, because this is a fiction, I don't need to justify the empirical correctness of the past hypothesis. I'm just setting up a way things could be as a warm-up exercise. In this setup, PHM says the initial macrostate, and here I'm sort of just borrowing a dilute gas kind of notion of macrostate, where the macrostates are characterized by the fraction of the particles with any given sort of coarse-grained velocity and position distribution. The initial macrostate is a spatially uniform distribution of particles, and for simplicity, they're all at rest. So at the beginning of time in this model, the particles are evenly spread out and they're not moving much. And pH mu says, it's really just the same version as Albert has, the probability distribution over microstates compatible with the initial macrostate is Liouville uniform. So this is, I think, very close to the detailed idea of what the Albert framework is supposed to deliver to us. And the uniform distribution, well, again, is really, I'm just putting it there because it's convenient for my fiction. I won't give much further justification to it. But it's worth saying a lot of the literature on thinking about the past hypothesis has thought that in the context of gravity, it actually makes sense for the low entropy state to be a uniform state because of ways that gravity work, which we'll come to very shortly. So let's talk about, let's talk about how the dynamics of that plays out. The dynamics is critically dependent on the sign of G. So I cunningly put a coefficient G into... There's a slight delay between my laptop and the screen. I cunningly put a coefficient G into the equation, but I didn't tell you its sign. If its sign is less than 0, which corresponds to a repulsive force, the dynamics here is extremely boring. The system basically stays in its initial macrostate. In a bit more detail, suppose randomly the particular microstate we choose is such that in some corner of the vast box, the particle density is a little bit higher than average. There's slightly more particles in this region than elsewhere. Well, you can see that that's going to be self-correcting. Because I've clumped the particles together a bit, they're going to push each other apart a bit. So small fluctuations in the system will damp right back out again. So basically, the state I wrote down was an equilibrium macrostate, and the system will stay for eternity at or very close to that equilibrium macrostate. This is a very boring cosmology. Things are a lot more interesting if we make G greater than 0, if we actually have in mind a gravitational interaction, if we make the force attractive. In this situation, small fluctuations don't get damped out, they get magnified. So if I have this little clumping together of particles, then of course there's a little bit more particles here, so there's a bit more gravity, so more particles fall onto it. To be slightly more technical about it, there is a thing called the Jeans instability in gravitating systems, where above a certain length scale, which is set by things like the density and average kinetic energy of the system, or rather below a certain length scale, then ordinary kind of kinetic pressure things will tend to damp out fluctuations. But above that length scale, fluctuations will magnify. And they'll magnify exponentially. And so provided the system is anisotropic on length scales large compared to this length scale, then however small those initial anisotropic fluctuations are, they're going to grow exponentially. So the system's increasingly going to displace clumping. And borrowing a term from realistic cosmology, we can call that structure formation, the formation of interesting sort of clumps and bumps in the distribution. And of course, as a consequence of the two parts of the past hypothesis, the system is always going to be a little bit anisotropic on any length scale you like, because the set of configurations where the matter is exactly uniformly distributed in space, right down to the micro level, is going to have measure zero in the total set of configurations. So every configuration is going to display a little, modulo measure zero configurations that we rationally set aside, every configuration is going to display a little bit of anisotropy on every length scale. And so every configuration is going to seed anisotropies that lead to the building up of structure. How fast does that happen? Well, it doesn't really matter because this is fictitious and there's no physically salient length scale in it. But it will happen exponentially quickly from however low the starting point is. And notice it will also happen macro-randomly. If I take that self-same initial macrostate, and I imagine preparing many copies of the system using pH mu to select the microstate, different versions of that will become inhomogeneous and anisotropic in different ways. And so you can see we get out something that's very much what Albert's framework wanted us to have, which is microscopic probabilities being magnified up to macroscopic stochasticity. So I would suggest that that model very much realizes as a toy the kind of things that are supposed to be happening in Albert's picture of the past hypothesis. But they also show up something interesting about the past hypothesis, which is that they flag that kind of division of labor between a macro and microstate assumption and show that in this case, at least, it's kind of dispensable. Because we could say, rather than have a macro hypothesis and a micro hypothesis, we could simply have a uniform probability hypothesis. We could say that each particle, independently, is randomly distributed in space and has some random distribution of velocity as well. So if we do that, if for all of our however many 10 to the power 100 particles, we suppose that each particle is independently randomly located, then we've stated a microphysical assumption about the probabilities that bypasses any need to talk about macrostates at all. Because, of course, if I make an assumption of that kind, then just on law of large numbers grounds, with a very high probability, and exactly how high will depend on exactly how coarse-grained our macrostates are, but with a very high probability, then PHM, as I originally stated, it will come about because the macro distribution is going to be very close to uniform if I use this probability distribution. And it entails, of course, the pH mu, the micro distribution. So we see, in a sense, if we have this kind of model, that we can avoid being caught up in any need to talk about macrostates at all. We can write something sharply microphysical that's adequate to derive the cosmology of this fictitious world. I mention this partly because it shows that circularity, however virtuous or otherwise it is, that we saw earlier in the past hypothesis, is in some cases dispensable. Okay, so much for fictions. Let's talk about some actual cosmology now. So for the rest of the talk, the things I want to talk about are models of the world that I think are physically realistic within their domains of application. Heterodox enough in various bits of philosophy of physics to think that it's a good idea if our models actually do model bits of the actual world. In Oxford, that's largely uncontroversial, but I hang out on the east coast of the United States. Things are otherwise in some places. So here's a little bit of classical Big Bang cosmology. The basic starting point we have is the FLRW, Freeman, Lemaitre, Robertson, Walker cosmologies, modified if you want by cosmological constants. That's not going to come into this story. I'm supposing that I have an expanding universe. Its space-time is homogeneous and isotropic, and it's filled with a homogeneous and isotropic fluid. Now, I should say, when I say this theory is classical, there's a certain sense it's classical by courtesy. Our equations of state of that fluid are very quantum mechanical in their nature. But in any case, according to our quantum descriptions of that fluid, initially it's opaque to light. It's expanding and cooling. At one point, it's a sort of plasma of quarks and gluons. Then it settles down into a plasma of protons and electrons. Then it settles down into a rather colder plasma of protons and electrons. As long as it's a plasma, then light can't pass through it. There's lots of charged matter. Electromagnetic radiation interacts with charged matter, so the plasma is opaque. Around 380,000 years after the Big Bang, the plasma cools down enough that electrons and protons start combining to form neutral hydrogen, and in 25% of cases neutral helium. And at that point, the fluid becomes transparent. And from about that point onwards, we don't really need to care about the fluid dynamics of the fluid. We can just treat it as something quite close to a dust, to crude approximation. And so from about that point onwards, up roughly to the point at which stars form, because stars need quantum mechanics too, we can just treat this as an essentially classical cosmological model. I mean, again, at first pass, again, those are the sort of broad, crude details. If you want to get into the detailed quantitative modelling of structure formation and into the astrophysics of that, then God help you, because it gets hideous and lots of aspects of quantum mechanics are relevant. But at the grain of description I want, we can just pretend it's classical. So, what happens to that initially homogeneous isotropic fluid as it expands? Well, we have some hints for this from our Newtonian fictitious model. In a gravitating system, small anisotropies tend to magnify. And the assumption that underpins this part of the Big Bang theory is very much that small anisotropies and inhomogeneities in the fluid distribution magnify and become large anisotropies and inhomogeneities, and that leads to the kind of structure formation that seeds galaxies, galactic clusters, and seeds the very rich, complicated structure of the universe we see around us. This is relatively recent sort of map of what the universe looks like at the larger scale. You can see that while it's kind of approximately homogeneous, there's a huge amount of detailed structure and sort of filamentary structure forming. And if you kind of zoom in on that structure, it becomes almost fractal, and you see more bits of this structure and subparts of that structure. So, crucially, and this is where it matters that we're doing a realistic physics and not just a fiction, while it's true that even microscopic fluctuations would eventually seed macroscopic fluctuations, then to seed the actual structure formation of the cosmos we see around us, that process is insufficiently quick. It has to be the case that even at the point of transparency, the universe was already somewhat anisotropic, somewhat inhomogeneous. And in fact, we don't just need to posit that to explain the macroscopic structure we see around us. We can actually see those anisotropies and inhomogeneities directly, because at the point at which the universe became transparent, it became transparent, and so light stopped bouncing off stuff, and until eventually it found its way to our telescopes. And so we can basically literally see what the universe looked like 380,000 years ago, and it looked like this. This is the W map of the microwave background radiation. It's very nearly homogeneous and isotropic. This heat map substantially exaggerates the inhomogeneities and isotropies, but they're there. So the red spots here are where the microwave background radiation is a little bit hotter than the average, and the blue regions where it's a little bit colder than the average. And you can see here that the distribution looks kind of essentially random. I mean, you can squint and you can see interesting structure in it, but it's characteristic of random distributions of data that the human eye squints at it and sees interesting structure in it. If you analyse this, for instance, by taking the Fourier modes of this and just looking at what the kind of distribution of each of the modes is, you can see it looks very much like it's random data with a particularly describable random signature. I mean, modulo the fact that actually it's got a massive anisotropy because the Earth is moving relative to the background, so you have to subtract that off. But with that done, very close to, but not exactly, isotropic and homogeneous, and the deviations from it look random. So then we can ask, what's the right kind of past hypothesis to make sense of this cosmology? And we should note in saying this that there's going to be something slightly artificial about this, because we're sort of asking, well, what should we suppose the initial macro and microstate would be at the transparency epoch? But it would be odd to make that a basic posit of our physics, because of course we'd assume that the state of the universe at the transparency epoch was to be dynamically explained by the state of the universe earlier than that. So there's a sense in which it wouldn't really make sense to permanently stop and say, a basic assumption of our fundamental physics is this is what things were like at the transparency epoch. But nonetheless, it's as far back as we can go, I think, while staying within the regime of classical cosmology. And it's a good exercise to ask, in order to get all the physics, including macrophysics, right from the transparency epoch on, what posit would be necessary for the transparency epoch state. So that's what I mean when I talk about a past hypothesis here. It's a Big Bang plus 380,000 years hypothesis. And it's going to come in two parts. And both of them, interestingly, are probabilistic. So PHM is going to say the initial macrostate is an almost uniform thermal state, and it's selected randomly from a certain probability distribution over almost uniform states. Which probability distribution? Well, the one that the normal inferential procedures of cosmology have in fact delivered to us, and I haven't got the closed form mathematical expression of it on the board, but it is a known expression that you can read off the data. But notice, this is now a stochastic assumption, or probabilistic assumption about macrostates. We're not making a categorical PHM in the way of Albert's assumption. We'd have to make a probabilistic PHM. And pH mu then has its normal form. Given the macrostate itself selected probabilistically, we select the microstate uniformly at random with respect to the Liouville measure compatible with the macrostate. And I want to claim that that kind of apparatus is about right as a description for how you would think about the classical cosmology in its own terms. And you can perhaps now see what I mean when I said that I thought the basic ideas of Albert's framework come through this analysis unscathed, but a lot of the interesting details change. Because you can see that while Albert had a sort of clean categorical macrostate assumption, probabilistic microstate assumption, we've had to bring probabilities in both to the macrostate and the microstate. We've also seen that while the fictitious Newtonian model eliminated talk of macrostate has come roaring back again as soon as we try to study the classical Big Bang cosmology. However, you may have heard this, the world is not classical. Let's now talk about how things would be in a quantum setup. And here I need to pause briefly and talk a little bit about the difference between statistical mechanics generally, or at least the kind of version of statistical mechanics that's underpinning Albert's framework, when we move from a classical context to a quantum context. And the crucial thing that matters here is that the notion of macrostate changes subtly but importantly between the classical and quantum case. So in classical mechanics, macrostates are, or at least if you like, are represented by subsets of phase space. You take the whole phase space, you partition the phase space into regions, those regions are your macrostates, perhaps up to measure zero issues about the boundaries of those macrostates. Every point is in one macrostate and only one macrostate. In quantum mechanics, the natural analog is to say that the macrostates are subspaces of Hilbert space. In other words, we have our extremely large dimension of Hilbert space that models my statistical mechanical system. Could be a box of gas, could be the universe, could be something in between. We identify subspaces that correspond to particular macro conditions, and we decompose the Hilbert space into those subspaces in the sense that the Hilbert space is the direct sum of those subspaces. And superficially, it looks extremely similar to the quantum case, to the classical case. But then you look in more detail, and you note, so firstly, that because of the way quantum mechanics works, while it's true that every point in phase space lies in one region, in one of these subsets of phase space, it's absolutely not true that every vector in Hilbert space lies in one of these subspaces of Hilbert spaces. Many of these vectors are going to be macroscopically indefinite. They're going to not lie in a single space. They're going to be superpositions of states with different macroscopic features. And even if we start with a macroscopically definite state, it's in many contexts going to evolve into a superposition of macroscopic states. And this is, of course, just the quantum measurement problem, because, for instance, if one of the macrostates could be described in macro language as situation with a cat in a box with a vial of poison, and two others could be described as cat where the poison has broken and the cat is dead, and cat where the poison hasn't broken and the cat's still doing fine, then Schrodinger's eponymous thought experiment evolves the state from a state that's definitely in the first macrostate to a state that's a superposition of lying in the second macrostate and lying in the third macrostate. And one solves the quantum measurement problem either, well, in this rather realist context where we're sort of unavoidably cosmological, one typically solves the measurement problem either by changing the physics in some particular way, by adding some kind of law of dynamical collapse, which causes the system to jump directly into a macrostate, or adding some additional hidden variables whose job it is to say what the real macrostate is, even while the quantum state doesn't say. Or one solves it by something like the ever many worlds move, which is, by the way, the correct way to solve it, where we identify this superposition of different macrodefinite states as telling us that the world has evolved into a superposition of quasi-classical states that we can think of as a collection of quasi-classical worlds. It's not really going to matter for the sake of this talk how we solve the measurement problem, but the problem will be there. Okay, but one crucial thing that comes from this, however we solve the measurement problem, is that, of course, in this quantum mechanical framework, there's a quantum mechanical notion of probability. In classical mechanics, you don't get probabilities out unless you put them in. If I just consider the evolution of individual points in phase space, nothing takes me from that description to an evolution of probability measures over phase space. But probability is just built into the quantum formalism. However I solve the measurement problem, I have to solve it so as to legitimate claims like when I have a superposition of, as it were, root 3 over 2 cat alive plus 1 over 2 cat dead, that can be interpreted some way or other, or can be dynamically modified somewhere or other to bring it about that, it's 75% likely the cat is alive and 25% likely the cat is dead. So a quantum statistical mechanic actually has, in the face of it, two notions of probability in play. Maybe a statistical mechanical notion, which tracks the fact that somehow, well, to put it in provocatively epistemic terms, we don't know which microstate the system's in. And a quantum mechanical probability that comes from the fact that even if we specify the initial microstate entirely precisely, it will evolve into a macroscopic superposition of many microstates, where we have to interpret the amplitudes of those macroscopic superpositions as probabilities. And in fact, it creates the possibility that in some sense, the quantum probabilities could crowd out the statistical probabilities. That actually, all of the probabilities we find we might need in statistical mechanics end up being quantum mechanical in nature, and there's no additional need for the statistical probabilities. And I think there are many reasons to think that that's true in just the ordinary playing out of quantum statistical mechanics. And we're going to see that in the cosmological context, it's something that's very naturally pushed on us by the way quantum cosmology works. So let's go back to quantum cosmology, having done that sort of ground-clearing work in quantum mechanics. And I want to distinguish sort of three notions of quantum cosmology we might have. And here I'm working backwards in time from later to earlier. The first bit of quantum cosmology you might call the electroweak epoch. And this is the period that runs from about a trillionth of a second after the Big Bang forward to, if you liked, the transparency epoch. This is the period of known physics. This is the period of electroweak symmetry breaking, of partial nuclear fusion to form helium nuclei from hydrogen, from protons and electrons. Eventually, the route to forming atoms and the plasma becoming neutral and reaching electromagnetic transparency. We understand the physics here really very well. We know how to calculate in this regime pretty well. We have a lot of data that supports the fact that our story about what's happening in this epoch is about right. It's not really very controversial. Prior to that, we get what you can call the inflationary epoch. I mean, I should say there's room for more bits of physics we don't know between the inflationary epoch and the electroweak epoch, but the interesting stuff happens when we get to the inflationary epoch. This is a period that's dominated by the so-called inflaton field. The inflaton field drives the universe to expand exponentially. This is a somewhat well-understood extrapolation of current physics. The basic idea is a quantum field theory, which we understand quite well, but the details of that theory are speculative. There is some support from data for this approach, and I'll come back briefly in a minute to what some of that is. the ideas of cosmic inflation are very widely supported in contemporary cosmology, but by no means universally supported. And the evidence is by no means conclusive. It's much less strong than for the electroweak epoch. Even earlier, you reach the Planck epoch. And this is the point where the whole quantum field theoretic paradigm for doing physics breaks down, the whole things are playing out on a space-time background breaks down, the whole we can treat general relativity as a quantum field theory at low energies breaks down. The physics in this regime is speculative. It's not under calculational control, which is to say, insofar as we have theories of this region, we don't understand them well enough to be able to calculate with them to a large degree. There's extremely little observational evidence that constrains this region, and there is absolutely no consensus as to how to do it. There's no consensus between different programs, and if you look at the strong majority programs and string theory internal to those programs, there's no consensus as to how to think about cosmology. As a digression, it's roughly true that if you are sympathetic to string theory, then we currently have theories of quantum gravity, but not theories of quantum cosmology. I'm going to focus on the middle of these three, the inflationary epoch, because that's about as far as we can go back while having a strong enough understanding of the physics to actually say some detailed quantitative things, and while saying something that at least reflects the sort of majority position in physics. It might be worth pausing to remember our project here. The idea here is to look at what kind of thing cosmology is delivering us for the past hypothesis. We haven't got a completed cosmology, so we don't expect a completed answer, but we want to see if moving from a less realistic to a more realistic physics changes the nature of the project as cashed out in the original Albert Mentaculus. So let's talk about this. And the crucial thing we need to understand to think about how the inflationary cosmology works is my setup is something like, I can go into details of this in the questions, but I'll gloss over the details here. My setup is effectively something like I've got a classical space-time background, I have a quantum field on that background, the quantum field is evolving on that background, and the background is reacting to the quantum field. And so the crucial question in doing that in quantitative detail is, what is the quantum state on that background? Well, it's evolving unitarily, so it's the unitarily forward evolved version of whatever it was earlier. So what we really want to know here is, what's the initial quantum state on that background? What state do I put on at the beginning before I carry out the self-consistent evolution that gives me quantum cosmological inflation? So, were we doing quantum field theory on Minkowski spacetime, or flat spacetime, or more generally, for people who know this stuff, on any spacetime with a time-like-killing field, we can coherently define a vacuum state, which is not the state with nothing in, but it's the lowest energy state, because if my spacetime has a well-defined notion of time translation with respect to which the spacetime is invariant, I can use that notion of time translation to define an energy. The energy is represented by a Hamiltonian, and I can consider eigenstates of that Hamiltonian, and I can say that the lowest energy of those eigenstates is the vacuum, and because it's an eigenstate of the Hamiltonian, it's time independent. That's what the vacuum is in Minkowski quantum field theory. And in quantum field theory on an expanding spacetime, that's not available to me. The spacetime's expanding, has no time-like-killing vectors, is not invariant under any sensible notion of time translation. There is no Hamiltonian, and so there's no exact analogue of the vacuum state. But it does make sense to ask, what would a quantum state be like that looks like the vacuum on short timescales, or more accurately, asymptotically far into the past, looks like the vacuum on short timescales. And that state is sometimes called the Bunch-Davies vacuum. We could call it a local quantum vacuum state. And the normal posit that's used in calculations in inflationary cosmology assumes that the initial quantum state, at the point at which we start the calculations, is the local quantum vacuum. Notice that's a pure state. It's not that there's a whole macro state worth of local quantum vacua. There's one local quantum vacuum. That's the state. And what do we find if we actually calculate with this state? Well, the local quantum vacuum is initially homogeneous and isotropic. And the dynamics, and the space-time is homogeneous and isotropic. And the dynamics don't themselves build in any violations of homogeneity and isotropy. So the local quantum vacuum evolves into a quantum state that remains homogeneous and isotropic. But it does not remain macroscopically definite. In fact, what that state is it evolves into a state that's macroscopically indefinite superposition of a whole bunch of approximately classical matter distributions, each of which is non-homogeneous and anisotropic. So you can think that the symmetry of the state, the homogeneity and isotropy, is now reflected in a symmetry of the overall superposition of classical macrostates, but not in any single classical macrostate. If you want a model of this, and this is actually somewhat similar to how the actual math of this plays out, if you imagine balancing a needle exactly on its end, if it's classical, and I balance it exactly, and the situation is exactly symmetric, and the environment is exactly excluded, then of course the needle will remain balanced on its end forever, because anything else would violate the symmetry of the situation. And if the needle falls in one direction, then it must have been that the initial configuration was not quite symmetric and somehow picked out that direction. But if I do that same problem quantum mechanically, and I start with my needle in a wave packet state that's exactly symmetric and corresponds macroscopically to the needle being on its end, what that state will evolve into as a wave function is a ring around all the different classical ways it could form. And so the overall quantum state remains rotation invariant, but it's a superposition of different classical states, all corresponding to different ways the needle could have fallen. So you see that what you have in this situation is a case where the symmetry is invisible at the level of each of the individual classical outcomes. And then whatever your solution to the measurement problem is, tells you why you would expect only to see one of those classical outcomes. And in inflationary cosmology, this process, this branch relative anisotropy and inhomogeneity, is the origin of the fluctuations in the early universe that are then taken forward into the classical regime of the Big Bang to seed structure formation. And indeed, when I told you that there's some empirical evidence for inflation, the most persuasive part of that evidence is that inflation makes predictions for what the probability distribution should be over those fluctuations we saw in the cosmic microwave background data, and those fluctuations match experiment. It's not exactly a precision test, but it's certainly true that those fluctuations could have been such as to rule out the inflation model, and they don't, if they fit the broad contours of the inflation model.
5 minutes, David, is that right?
Yeah, that's fine. I'm almost wrapping up. And notice that probability distribution over fluctuations is entirely quantum. It doesn't have any statistical mechanical component. It started from a specific known closed form quantum state that you could literally write on the whiteboard. And it evolved that state forward, and that's the unitary dynamics applied to that known quantum state gave rise to that probability distribution over classical fluctuations. There's no residual space for statistical mechanical assumptions in that story. So, what does the past hypothesis look like on that story? Well, remind ourselves, here's the Albert framework again. We have the Newtonian law of motion. We have the past hypothesis that the world first came into being in whatever particular low entropy, highly condensed Big Bang sort of macro condition it is that the normal inferential procedures of cosmology will eventually present to us. And we have the statistical postulate. Here's what we have in the best bit of quantum, the most up-to-date bit of cosmology we currently have. We have quantum field theoretic laws of motion, which, to be sure, we don't fully know. We're not sure what dark matter is. We're not sure the details of the inflaton field. There's the past hypothesis, which is that the world came into being in whatever state it is that the normal inferential procedures of cosmology tell us it is, which is specifically the local quantum vacuum state, the Bunch-Davies vacuum. And there's no third component. There's no statistical postulate. In other words, we have, if we apply the Albert formula to our current state-of-the-art cosmology, we have a situation where all of the work is being done by a microscopic, precisely statable assumption about the initial state, and by the microdynamics. There's no need anymore for notions of macrostate. There's no need for notions of statistics. Everything comes out of the the microstates. It has to be said, incidentally, that our reasons for choosing the local quantum vacuum as that initial state are, as much as anything, convenience. And of course, it's probably the case that if we tried various other such states, more complicated ones, that they would also give rise to similar things. But that just tells us that the normal inferential procedures are pretty inconclusive about those fine details. It doesn't tell us that we need some distribution over possible states of that kind. I mean, notice that this is how quantum mechanics helps us. Classically, you can't get anisotropy out without putting anisotropy in. You can't get probability out without putting probability in. In quantum mechanics, there's no problem of supposing that the initial state is exactly isotropic, exactly homogeneous, and nonetheless gives rise to the observed anisotropies and non-homogeneities. So I'm pretty much done, but I just want to finish up by returning to David Albert's T-shirt. Because you can now ask, what is God actually going to tell us from the T-shirt, at least based on the current best cosmologies we have? And the answer to that is going to depend how you solve the measurement problem. If you like sort of dynamical collapse approaches to the measurement problem, then what's on your T-shirt is going to be the past hypothesis in the local quantum vacuum setup, plus the unitary quantum dynamics, and a large number of CERN graduate students and postdocs demonstrate that you can fit the standard model on a T-shirt if you write small, and you've got the back of the T-shirt to handle dark matter and the infiniton field. You better squeeze in somewhere a stochastic collapse law, if you like dynamical collapse theories, which will modify the Schrödinger equation so as to suppress macroscopic definiteness. We don't, by the way, have any such theories for quantum field theory, and this is one reason one should adopt the Everett interpretation. But suppose there was such a thing, you'd have to put that in. And notice that in the sense we were discussing earlier, this is the compromise between simplicity and strength. God doesn't have time to tell you all the details. There's quintillions and quintillions of them, and the stochastic numbers in the stochastic collapse law can be interpreted, if you buy the broader Albert framework, as the best succinct description you could give. If you like hidden variable theories, the T-shirt has the past hypothesis, the unitary quantum dynamics, the unfortunately non-existent Bohmian guidance equation for quantum field theory, and the probability distribution over the hidden variables. That's the analogy of the distribution we see in something like the de Broglie-Bohm theory. And again, this is the compromise between simplicity and strength. If we like the Everett interpretation, then the T-shirt contains the past hypothesis, i.e. the local quantum vacuum, plus unitary quantum dynamics, and nothing else. And there's no compromise. The Everettian God says that, asked by David Albert, what's the universe like, hands him the T-shirt and says, you'll be late for your next appointment. I'll stop there.